Good morning all, some new PCBs from JLCPCB, so let's get straight in there and take a look at what we've got. And this is really a very important PCB for me because it's the new version, the JLCPCB version of the PWM5 ThruHole. It says it somewhere, yeah, PWM5 ThruHole. And the reason this is so important to me is because this is really the only thing I've ever designed from the ground up, software and hardware, that became a product, and I actually sold about 900 of these things. So what is the PWM5 solar charge controller? Well, it's a device to which you connect a lead acid battery on red and black, a solar panel up to 100 watts on yellow and black, and this thing controls the charging of the battery from the solar panel. Now, for a lot of the time, this thing just switches permanently on and the solar panel is connected to the battery. But once the battery gets up to, on this device, 13.5 volts, this starts to pulse width modulate, hence the PWM, and it regulates the amount of, in terms of time on and time off, the amount of charge coming from the solar panel to the battery, so that the battery never goes over 13.5 volts. Actually, never is not the best word to use, because it does go over 13.5 volts in the morning as a little booster charge. But for the rest of the day, it's held at no more than 13.5 volts. Let's open this up and take a look at some of the features that I put on this board. And I know that there are things, even at this early stage, that I wish I'd done slightly differently. I don't know quite how I would have done them differently, so this is something that we can discuss. Incidentally, I've got lots of these things, 30, and I'm going to give some of them away. So let's have a close-up look at one of these boards. I'll bring the camera down so that we can get in nice and close. So what have we got on here? We've got the microcontroller. It's an 8-pin PIC12F683. It has A to D for measuring the battery voltage and PWM for controlling the Mosfet. There's the Mosfet. It's the IRF3205. It's run at no more than 6 amps because that's all that a 100 watt panel will produce. And that's because this is not heat sinked in any way. And I had to be sure that the temperature rise on this was never so much that the whole unit would overheat. And at 6 amps, this thing has sufficiently low on resistance that it doesn't overheat. Okay, what else is on here? We've got the LP2950 voltage regulator, 5 volts. That's a 1% voltage regulator. On the femto version of this, which is my little surface mount one, which is here, it's tiny. The regulator is 3%, and it does vary, and that is an issue, and I'm thinking about ways to solve it. There's a programming header here, 6-pin programming header, so that we can use a programmer. So that will plug on there. Pin 1 goes to the arrow, so that the chip can be programmed after it's been soldered into the board. But there are issues with that, and this is something I'm really interested to test. Can I program the chip with components attached to it? Because the programming rules say program the chip without components attached to it, but I kind of think it might be possible to program it with all the other components in situ. We've got some diodes, 4148. We've got some transistors here, 3 transistors, which make up the charge pump high side driver. Because the thing about this circuit, I will draw a simplified circuit in a moment, is that the Mosfet source pin is connected to battery positive, which means the gate pin has to go above the battery voltage. How's that done? With a little charge pump step-up generator. We got some capacitors and resistors. Now the resistors, I went to 1/8 watt. Because of the size of this board, I kind of limited myself because I said I want it to be 2 inches by 1 and no more. And that made it really quite hard to fit everything on. But that's just the way I think. The 20K there and the 82K are the potential divider, so that the chip can measure battery voltage, so they have to be 1%. I don't think anything else needs to be 1%. Here's the Transient Suppression diode, which takes high voltage transients coming in on the solar panel wires and clamps them, doesn't let them go over a certain voltage. Actually, this one is a P6K33CA, so it's 33 volts approximately where it clamps the voltage. And in the middle there is a blue LED, because the very first thing I did when starting to develop the software for this was to write a Blinky program, as you do. Now, a couple more things. I wanted holes in the corners. I couldn't quite go to 3mm because they just felt too large, so they're 2.5. That's a 3mm hole. That's actually for the Mosfet. Let's see if that fits. Whether I got that pitch right, it probably isn't quite right, but it doesn't really matter because it's not bad. I've no intention of using that hole because in actual fact, this transient suppression diode is designed to sit over the tab of the Mosfet to sort of hold it in place, kind of thing. It's slightly unconventional, but there we are. Now there are some high current tracks on here because I felt it was important to have points where the wires come in. So here's red wire VBAT, here's the yellow wire V solar. These two are the black wires. Let me bring my solar charge controller back in. Yeah, it's like this. We've got yellow and black in from the panel, red and black go to the battery. So you could say that's an output, but it's also an input because it uses the battery to power the electronics. So I wanted these points that you could attach wires. They're probably going to be attached on the bottom. In hindsight, I wish I'd put these labels on the bottom now, but never mind. 2 ground points there. Alternatively, instead of soldering wires into these holes, you can solder them directly onto the legs of the Mosfet. Don't cut them off and solder wires onto them. Then you don't need to use these high current tracks. Now these high current tracks take up to 6 amps. I figured this was about wide enough to do that, but in order to make sure, I duplicated them on the bottom, so they actually run across the bottom of the board and the top of the board, so it kind of doubles up the amount of copper. So why a through-hole version of this solar charge controller? Well, I went to the surface mount version, and some people have said, well, I'd love to build one of these solar charge controllers, but I don't want to fiddle about with surface mount components. I want something that I can actually see. So here is the PWM5 through-hole, just for you, well, and me. So this replaces the previous circuit board, which is this. It's a single-sided circuit board made by a local PCB company, and this was really laid out to replicate or mimic to some extent the original Vero board version of this thing. This is actually a prototype. It's slightly oversized. I shrunk this down a bit for the production units. So the production units went out as Vero board units. In fact, here is one. You can see this one's got Vero board in it. And then when that just became too much trouble, I had PCBs made by a local company, but they were about £1 each, so they were quite expensive. And that enabled me to carry on production until I got to the point where I just couldn't do it anymore, because I'm sure anyone who has done electronics assembly knows when you start doing very large volumes of it, it gets very repetitive. So what shall I do with this PCB in this video? Well, I think one of the first things I need to do is think about this resistor here, this 150 ohm resistor, which is actually the LED resistor. So it's just the current limiting resistor for that blue LED, which I put under the chip. I'm now not so sure about this. It might even have fitted up there possibly. But anyway, it's there on this version of the board. There is the possible... The thing is, I was assuming that the chip would be in a socket, but it doesn't really need to be in a socket, because if you solder it into the board and, I don't know, it loses its program or something, you can reprogram it because it's a flash chip. You could put that 150 ohm resistor on the underside, because there are going to be wires running into this unit, into these 4 large holes, the 2 black wires, the yellow and the red wires. So it wouldn't be a problem that being under there from a physical point of view. I might try putting a resistor in there and seeing how wobbly the chip is on the top. Perhaps I could just solder the chip a little bit high up on its legs, but that's where I'm going to start. I'm going to get a chip in there and think about that 150 ohm resistor. Now, I do have most of the components for this left over from when I was manufacturing them, but I don't have them in 8th watt resistors, but I have found a 150 ohm 8th watt resistor, so I'll put that in. I'm just going to put it in loose for the moment and put a chip on top of it and just see how wobbly that is. So while the soldering iron warms up, I said I'd draw a simplified circuit diagram of this. Now it's going to be really very simple indeed. I just need to look up the symbol for a Mosfet because I can't remember it. Yes, that's it. You show the gate like this, and there are 3 connection points, and this is the source. Now that goes to the positive of the battery, so it goes to there. 12-volt battery, 12-volt lead acid battery. This is ground down here, and I'm going to show the solar panel here as, I don't know, a series of lines in a rectangle that goes to ground, and that is a higher voltage, which I'm going to show as a higher wire, so the height of the wire represents the voltage, and that goes into the drain. Now you have the little arrow going in there, and of course there's also the body diode, which you can show going across drain and source like so. And that's really it, apart from a box of tricks here, which I will just call the clever bit, and that connects to the gate of the Mosfet. So the gate, and there'll be some ground reference there, of course. The gate is controlled by the clever bit in reference to the voltage across the battery. But essentially all this thing is a Mosfet switch, which either allows the solar panel current to enter the battery or doesn't, and it switches on and off at 122 Hertz pulse width modulation. So for my first one of these, I'm going to solder the resistor on the top side of the board. Well, I'm soldering on the bottom side of the board, but the resistor is physically on the top side of the board. This might be quite tricky because I know these resistors are very old and the legs are a bit tarnished, but that's one side of this is ground, of course, so we've got a heat dispersion issue here. Right, that's in. Let's crop that down. So I found this box. Now I've got a feeling these are programmed with the program firmware version 1F2, which means firmware 1.2. So I'm just going to sit one of these on the board and just see how it sits over that resistor. That resistor won't get warm because the software is designed to put the LED on for only a fraction of the total time, so that it doesn't use a lot of power. The whole point of this charge controller is so that it only drew 1 milliamp from the lead acid battery, a maximum of 1 milliamp. So let's put that in, just see how well it fits. So there it is, the 12F683, and yes, it does sit a little bit high with that resistor underneath it, but I don't think it's a major problem. On the next one I make, perhaps I'll put the resistor on the underside. Let's just try putting the Mosfet in, which lies down on the board like that. I mean, it's not a huge amount higher than that, and in fact the blue LED is going to sit a lot higher. Let's put one of those in. And there it is with the blue LED in place, and of course the blue LED is by much the tallest component on this board, so I think that's all going to be okay. You can see here where the blue LED is driven from this pin of the microcontroller. It goes through the LED, through that resistor which is sitting under the microchip, and to ground. So I'm going to solder the chip in, and I'm going to solder the blue LED in, and then if I put 12 volts to this board, or in fact any voltage, oh, I'll need the regulator, won't I? Yes, I'll have to put the LP2950 regulator in. I needn't, or I could put in the 100N, that's just across the power pins of the PIC, which happen to be pins 1 and 8. So yes, I'll put a regulator in as well. In fact, what's to stop me just putting 5 volts directly onto the chip? Well, nothing really. So here goes, 5 volts. The LED comes on for 2 seconds, and then it should, yes, I mean, the A to D converter has not got a proper voltage divider on it, so it's all over the place. But yes, it's showing a bit of PWM there, a bit of possibly monitoring of the battery voltage, but it's all over the place. But that's certainly the correct boot sequence. There is actually a 200 millisecond delay before the chip boots up, and then there's a 2-second period where the LED is on. So there's the short delay, there's the 2-second period, and then it goes into the program proper. So as far as the microcontroller is concerned and the LED, that's all working. So that's all good. I think the next thing I want to do is give this microchip the ability to run from 12 volts. I want to get the regulator in there. They are in here. This is the LP2950, and they're pre-bent to a 0.1 inch pitch, and I've gone for a component soldered flat to the board, so I'm going to have to bend those legs back to fit this in the board, but that's not a major issue. There's quite a bit of glue on these legs from the paper bandolier, so I'm just going to cut those off and shorten this down a bit. Let's see if that will go through the holes. Should do. Right, so that component can sit flat to the board. That's quite neat. These transistors, the 3904 and the two 3906s, are going to stand up off the board. I put holes. They're not 0.1 inch apart, they're slightly closer than that. But I actually designed that footprint because the one that came with the 3906s and 4s, it was just ugly. It had a big square pin for pin 1, completely unnecessary because there isn't a pin 1. There's a base emitter and collector. So let's get that soldered in. I'll need a 4148 diode there because that's the main feed into the power supply. It might seem odd thing to do to put a power supply into a signal diode, but this thing uses so little current that that's more than enough. Then I can put 12 volts across this thing and this should power up. Now I can't get the potential divider operating because I don't have 8th watt 82k and 20k. I have ordered them on eBay, but they'll take a little while to come in. I could put the charge pump components in, which are these 3 diodes, those 2 capacitors, which I have, a 1 microfarad tantalum there, and just see that the 20 volts or so, which is 2 lots of 5 volts, added to the 12 volts of the battery, courtesy of this charge pump. I can see whether that's there. That would be worth doing. So let's solder this regulator in. Pins are quite close together here, but because these are through holes, plated through holes, this is the ground one, which is always a little bit more tricky. It's a bit easier than just single-sided plated holes, because there you really do have to build up a good mound of solder. Here you can just let it flow through the hole. It doesn't need to mound up on one side. It's nicer if it does. Let's have a closer look at that actually. And they are, well, they're slightly over mounded, particularly the middle one, which is the ground. Yes, that is the ground, isn't it? Because we've got the 2 arms coming out to the 2 capacitors, but it's all right. I'm going to fit these 4 diodes now, these 4 1N4148s, and they are these 4 up here. One of them provides battery voltage to the regulator circuit. It's kind of an anti-reverse polarity diode, so if you put VBAT and ground the wrong way round, then the regulator circuit won't power up, the chip won't power up. The chip then runs square waves out on 2 of its outputs through these 2 capacitors and these 3 diodes, and that does a step up. It's a charge pump, so that the voltage that results across this 1 microfarad capacitor is 2 lots of 5 volts, so about minus diode volt drops, of course, so you've got about 8 volts on top of the 12 volts. You should get about 20 volts at this point here if the charge pump is running. So let's get these 4 diodes in, and then I can power up the chip and just check. I'll get all these capacitors in as well around the regulator and this capacitor to smooth the output of the charge pump, see whether we've got 20 volts there. So oh, that's cooled down. Let's get that back warm again. So if you would like one of these circuit boards, I'm going to give 10 away. Just let me know in the comments below that you'd like one and just a brief reason for why. Comment trolls need not apply. The 10 PCBs will go to nice people. So here are the 3 diodes that make up the charge pump. Here's the diode that feeds into the regulator. So I just need to solder those 3 in. Then I'm going to put on the smoothing cap on the output of the regulator. There's a little cap on the input of the regulator. That's the cap that smooths the output from the charge pump. And I need these 2 47N capacitors because that's where the 2 pins waggle backwards and forwards in antiphase to generate this high voltage. I'm going to pick that off there. So we should see about 20 volts there. Now, I wasn't sure when doing these capacitors whether to do them 2/10 or 1/10 or somewhere in between. So I ended up doing them 2/10. And the 47Ns here that I've got are bent to a 2/10 pitch. The 100Ns are actually a 1/10 pitch. That's got to go across there. So I'm going to have to bend those legs out to fit it in there. The 220p I think is also a 1/10 pitch. So if I do a Rev 2 board, and I'm almost certainly going to do a Rev 2 board, I might slightly adjust these capacitor spacings. The resistors I think I'm going to have to stick with 8th watt resistor pitch, because I just couldn't fit in the, I don't know, 1/4 watt or 0.6 watt or whatever they are resistors. They're just too big. So this 100N needs its legs bent out into a 2/10 pitch. Try and do that without cracking the casing too much. So let's bend that back, bend that back, see if it fits. One thing I didn't do, again, is I didn't put little pluses on my tantalum capacitor symbols, so you're going to have to look at the underside of the board and work out where plus goes. Well, there are no negative voltages on here, so you won't have that problem. Basically, plus is where there's a track, minus is where it goes to ground, which applies to those two. And this one that I'm about to solder in, positive is where there's a track, and ground is where the spokes run out to the ground plane. Well, I think that's everything I need to get the charge pump working. VBAT goes in here, runs up there, runs through that diode into the regulator circuit. We've got input and output capacitors, 100N. We've got the charge pump, diodes and capacitors, and a smoothing 1 microfarad on the output of that. So we should see, if I put 12 volts on here, about 20 volts on that. I think it's the, oh, I can't remember, is it the emitter of that transistor? Something like that. Let's power it up. So I'll put some wires on here with clips that can go to a battery. I think I'm just going to power this up briefly with a sort of higher resistance battery, just in case there's a problem. There shouldn't be. So let's put 0 volts on there, plus 12 on there. So the light comes on, goes off, and then we should get some random flickers. So that looks all right. So I think what I'll do now is put it on a big lead acid battery where I can make these connections a bit more permanent so that I can check whether this charge pump is working. So let's see if that light comes on again. There's the blue LED, that goes out, and now I should be able to pick off that 20 volts. So let's get my DVM. Okay, right, ground can go back all the way to the battery. You need to see the display. The high voltage should be on this pin here. It's not. Why not? Oh, because I got it on my 10 amp setting. That shorted out the high voltage charge pump, but that shouldn't matter. Oh dear, that blew the 5 amp fuse. 5 amps? Let's get a new fuse. Ah, yes, of course, we have a direct path from VBAT through to that point. So if I shorted that point out, then yes, we would have got a lot of current through these diodes. I wonder if they survived. Okay, let's find out. Black to 0 volts. Plug that in there. Ah, 12.4 volts. That's interesting. That implies that the charge pump is not running. Oh. Right, let's check these diodes. Positive to anode, 0.5 volts, that one's okay. Positive to anode. Ah, that one's a short. I think I might have taken a diode out. Oh, that one's a short. And I think I've blown all three of those diodes. I shall just replace them. And the moral of this story is always check whether your meter is in, the connections are on the 10 amp current connections when you're trying to do voltage measurements, because it blows things up. Now I've got to suck all these holes through. Oh well, lesson learnt. Let's bend some new diodes into shape. I managed to get all the solder out of the holes. These diodes don't bend into a nice shape. They kind of kink over. It's very odd. Oh, that one's gone into a nice shape. Right, I'll stick those in and we're done. Silly schoolboy error. Right, let's make sure that's set to not the 10 amps position. We're on volts. Okay, let's have another go at measuring this 20 volts. I'll put that on ground over there. And this goes on that connection there. And we've got 21.5 volts. So yeah, the charge pump's running. 12 volts is being boosted up to 21.5. Awesome. It's interesting. This LED is actually showing a voltage, 11 point about 8, but it can't possibly be doing that because the potential divider resistors aren't in there. So it's just got a floating voltage on the A to D input, and it just happens to be, well, that one was around about 12.5, which is what the battery is, but doesn't mean anything. So that's as far as I'm going to go today. I've got the chip running. I've got, well, you can see that the voltage measurement thing, flashing LED type arrangement is working. The 20 volts or 21.5 volts of the charge pump is there. The chip's clearly running. The 12 volts down to 5 volt regulator is all working fine. So back to these 10 surplus boards. As I say, put a comment in the comment section below the video and I will pick 10 people. I'm not going to do it randomly, I'm going to do it by choice. I might possibly on this one go for UK rather than overseas, just because of the postage situation. But if you make a good case, well, I might be prepared to pay a little bit more and send them off to USA or wherever you happen to be. Please make sure that your YouTube account is not locked down. If it's totally locked down, I won't be able to contact you and you won't get a board. So make sure I can get in touch with you through the messaging system of YouTube. So that is my new PWM5 ThruHole PCB. So far it's looking good. It almost certainly will go to a Rev 2. I should say a big thanks, of course, to JLCPCB who sponsor these videos and provide these PCBs. And I'll do another PWM5 ThruHole video very soon. Cheerio.